In previous videos, we looked at this wave pattern that we've received through various oscillations, such as in a spring or a pendulum, or even a slinky that was given a little shake, and we watched the energy travel down through the wave. And remember that waves don't move the particles. What they do is they transfer the energy. The particles basically stay where they are. So this piece of the let's say it's a string will move up and down, but that piece of the string doesn't end up over here later. It stays right where it was, just moving up and down and oscillating. Okay, so a couple more definitions that we need to understand. The bottom part of the wave down here is known as a trough. Okay, so the bottom of the wave is the trough. And the top of the wave, right here, is a crest. So I know my surfing friends, you know who you are. You're looking for the crest of that wave usually. That's where the fun begins. And the distance, once again, between two places on the wave that's the same. So let's go from crest to crest. That is our wavelength. Or it could be from trough to trough. That's our wavelength. It could even be from here, but that's not a wavelength there. Here's the wavelength right there. We could go as long as it's between, here the wave is coming down, here the wave is coming down. We're just going to need to make sure we're in the exact same place to be one wavelength, represented by lambda. There are some fantastic web simulators to look at waves and their behaviors. One of my favorite is the PhET Colorado site that you see here. When I create a wave impulse, similar to what I did in the classroom, you can see the wave travel down through the string. And in this case, it's just going out of the window. There's nothing there to stop it or do anything. So I have no friction, no resistance. The wave stays the same height the entire way, and it goes along. If we had some damping, damping is basically friction. It's a loss of kinetic energy. And you'll see that as the wave goes along, it gets weaker and weaker and eventually disappears. Now, this is the normal situation that would happen with waves. We don't have anything that's 100% efficient. But to understand the waves, I'm going to leave it turned on as if we have zero damping. So I've got this wave pulse being generated. And at the other end, it just keeps going forever out the window, and who knows where that wave goes. Now, what would happen if we had it tied to a wall or it's fixed in place? What happens? And so we're going to get some reflection going on at the end here. And so reflection is one of the next topics we're going to talk about. When we have a fixed end, you're going to see that the energy of these little particles of our string, okay, we have upward momentum, then we're going to have downward momentum. And what's going to happen is that downward momentum is going to continue because there's no damping. There's nothing slowing down the downward momentum. So what happens is that now we have the wave being passed underneath the string. So what we have is we have an inverse of what we had before. We had it on top, it hit a fixed end, and it came down underneath. Once again, I have another fixed end here. So what do we expect to happen? We expect that the momentum of these balls, as we incrementally move through what's going on here, they're going to have momentum upward. And because there's momentum upward, it's now going to continue along the top. And of course, this pattern is going to repeat itself. It hits a fixed end, switches under, and it keeps going. What would happen if this end on the right was not fixed, but it was allowed to move up and down? Well, then what we're going to have happen is that the momentum is actually going to cause the end of the string or this wave to move up with it. So the momentum is transferred into the end. And maybe it's just hooked on here loosely, or a little piece of string tying it on. And what happens is when it comes back down, that energy is transferred back into the spring, and you're going to see that it travels above on the way back. Now, of course, on the left side, it's a fixed end, so what's going to happen is it's going to go down below again. Okay, so it's really important to understand what happens at a loose end and what happens at a fixed end in terms of the wave. So once again, if there's a fixed end, it flips it over. And if there's a loose end, it comes back on the same side, above or below. So as we briefly look at what reflection in a wave is, let's just make sure we cover a few definitions. First of all, our normal lines, rays, angle of incidence, angle of reflection. So the green is my wave approaching, and it's going to hit a solid barrier here, like a wall or something. And what would happen as it hits that wall? Well, what we would know is that it would bounce back. But really what matters is whether or not the wall was perpendicular or not. So the red line here is the ray of the energy. This is the direction that the energy of the wave is being passed. And if it comes in and hits the wall that's square, then what would happen is that it would reflect off. See if I can get this. There we go. But what if the wave was tilted, or sorry, the barrier was tilted? So what we need to recognize is that we can have different results. So what I have here in the magenta, purpley pink color is what's called a normal line. This is my normal line. And it is at normal is 90 degrees between the normal and the barrier, whatever it's hitting. Okay? So it is a right angle triangle. Or I should say a right angle. The angle between the ray and the normal line, this angle right here, is my angle of incidence. This is my angle of incidence. I'll draw an arrow. Say that's my angle of incidence right there. It's between the ray and the normal line. So what would happen with this wave in green? Well, as it hits this barrier here, it won't bounce straight back. What will happen is it will bounce off at an angle. And we'll draw that here in blue. It will bounce off basically in this direction. And what we're going to see is that the angle that bounces off at, this angle here, is your angle of reflection. So the angle of reflection is between the normal and the ray of reflected waves. So that's the angle of reflection. And the angle between the incident ray and the normal line is the angle of incidence. And these angles will be equal. So the angle of reflection is going to equal the angle of incidence. Refraction refers to some sort of bending of the wave. And there's many different simulations and scenarios that you can investigate that shows this. But one example is that, if I go to the beach and you'll see there's a little sandbar. Oops, that wasn't a good sandbar. And here's my wave, and my wave is approaching, and this is the crest of the wave coming in as my wave goes this way. What's going to happen as this wave hits the sandbar? Well, some of the wave is going to bounce back, but some of it's going to travel through the little gap in the wall here. And what happens is that waves tend to bend and form these curves as it goes through that little gap. Okay, so this is a form of refraction. Another scenario you might think about is, let's say here's the shoreline and there's a little piece of land that sticks out. And what happens as the wave comes in towards this? So once again, here's the crest of the wave. The wave's coming towards the shore. And as it gets close to this crest, these waves here are going to keep going fast, but these waves here slow down around the land. And so we got this bending here of light. Or sorry, not of light. What happens with light as well? Or does it? But we have this refraction. It's the bending of the wave. And we're going to start by looking at just thinking about waterways, but how does this apply to sound or... So the last topic for this video is to look at what happens when waves run into other waves. So if you recall, I had an impulse here on a wave, and it travels down through the wave. Depending upon if this is a fixed or open end, it'll reflect back. So the question now is, what if there's a second wave? So I'll launch a second wave here. Okay, so I've got one wave on the bottom. I've got one wave on the top. Now let's go to slow motion here. So these waves, if I was to take my ruler here and measure, I can see that this wave is about 1 centimeter high, and this wave is, I'll call it 1 centimeter high as well. It's 1 centimeter low if you want to say that. So the amplitude here is 1 centimeter. So it's 1 centimeter from the midline to the top and midline to the bottom, from the midline to the crest, midline to the trough. Right now, these waves have not hit each other. But as they start to approach each other, we're going to have a moment in time when they're exactly on top of each other. And that moment of time is called a superposition. And what we want to know is what happens during the superposition. I'm going to play here, slow motion. Okay, so right now we're just hitting that moment. We have this upward wave. This ball here is pulling up. Right here is pulling up. This ball is being pulled down. The crest and the trough are not quite aligned yet. Just another moment. And what's going to happen? I just missed it. But what happened is that there was no wave here for a brief moment. And then the waves continue. You'll see this again happen here in a moment. So as they approach each other, did you see it? And for a brief moment, there was no wave. See if we can get it one more time. So there's this moment where the wave that's above and the wave that below they cancel each other out. Their energies cancel each other out momentarily, and then they pass through each other. When they cancel each other out, that is referred to as destructive interference. So there's an interference and it's destructive. And when it destructs, there's loss of energy, or the amplitude of the wave is momentarily changed. So now the question is, what happens if they were on the same side of and collide it together? So let's go to a loose end. Okay, so what's going to happen here? Let's go to slow motion again. Okay, this green ball is being pulled up by the red one there. Have to wait till they're back on the top together or on the bottom together. Oh, here we go. Go into slow motion. And you'll notice that here we had an amplitude of 1 centimeter and 1 centimeter. And what happens is now we're looking at an amplitude greater than a centimeter. In fact, it doubled in its amplitude. This is known as constructive interference. It's when the two waves collectively add their heights together. Here we have two scenarios. We have two waves moving towards each other. In the top scenario, they're both on the top side of a wave, or on top of the wing of a string. And in the second scenario, one is above and one is below as they approach each other. So the question is, what happens at this superposition when these two waves meet? Well, let's assume that they meet sort of here in the middle. This wave, magnitude 5, and this wave, magnitude 3, will create this big wave in the middle momentarily, and it will have an amplitude of 8. In the second scenario, what will happen is when they meet, they will cause destructive interference, and what will result is a small wave on top, and this will have an amplitude of 2 centimeters. Once again, this will be what we call constructive interference. And in this case, we'll have destructive interference.